to you for senior intermediate. We're going to start off with similarity, and then we're going to move on to the angle bisector theorem, and then Heron's formula. And these three are basically all triangles, so good luck. And finally, we move on to 3D geometry. So as you know, our first topic of today is similarity. But before we get into similarity, let's focus on congruence. Congruence is basically when there are two polygons, two or more, that have all congruent angles and all congruent sides, meaning all the corresponding sides and angles are congruent. Congruent means equal or the same. So if you place one on top of another, you should see only one figure. And then there's similarity, which is sort of like congruence, but sort of isn't. It's basically when all of the corresponding angles are congruent. Remember how I said corresponding? Corresponding, that word is important. And the sides in similar polygons aren't necessarily congruent, but they're proportional. So they have a ratio between the corresponding sides, and that ratio is called the scale factor. In a set of congruent polygons, the scale factor is 1, meaning when you take one into another, you're just multiplying it by 1, and multiplying by 1 gives you the same thing. If you want to make something smaller, you multiply it by a smaller scale factor of fraction, something less than 1. If you want to make something bigger, you multiply it by more than 1. So now we move on to the triangles part in similarity. So triangles have their own set of rules that make it way easier to figure out which ones are similar and congruent. So we'll start off with 2, because that's all I can fit on the board. So we have angle, angle, and if you want to write it on paper, it's AA or AAA. And basically what it says is if two corresponding angles in a triangle are congruent to one another, then those two triangles are similar. So what this means basically is that whenever you have 3 angles that are the same as another one, that means the sides are automatically going to be proportional. There's a whole theorem on that, but we're not going to get into that. So the third side's always going to be congruent to the corresponding third angle is going to automatically be corresponding to the corresponding third angle. I cannot speak today because of the triangles add up to 180 degrees. If 2 are congruent, they're going to have the same sum as the other 2, and automatically the last one, they're going to be equal. Then we move on to side, side, side. Now if you have 2 triangles that all 3 sides are congruent to each other, that means those triangles are congruent. But if they're proportional, that means they're similar. So from the sides, you get that the angles are also congruent. And same thing with the proof. There's a whole proof on that, but we're not going to get into that. So, for example, I am a terrible drawer. I suck at drawing, so good luck. So these 2 triangles, this is supposed to be smaller than that, but they're supposed to be similar because these sides are all proportional. And these are congruent because these corresponding sides are all equal. Now you might be confused about what I say in corresponding, so let me just show you what it means. When you have 2 triangles like this, these 2 angles would be corresponding. These would be corresponding, and these would be corresponding. In return, these sides are corresponding, these sides are corresponding, and these sides are corresponding. Now, let's move on to our final triangle rule. And that is basically the side angle side, or SAS. And in this, 2 triangles are considered similar if 2 sides and the angle between those 2 sides the sides are in proportion and the angle is congruent. So here we have 2 triangles. Like I said, I am terrible at drawing, so it'll have to do. In between these 2 angles are 40, and that fulfills our angle requirement. There was a block. So these 2 are congruent, so that fulfills our angle requirement. And as for the sides, we have 3, 3, 7, 7. They're already in proportion, 3 to 7, 3 to 7, meaning that this triangle is, in fact, these 2 triangles are similar. Now let's move on to right triangles, which have an interesting case. If you have a right triangle, this may be hard to see here. A, B, C, C is at the right angle, with sides A, B, and C each opposite of their said angle, and then you draw an altitude from C down to AB. Let's call that altitude H. And when you draw that altitude H, you draw it down to the point H. From there, C splits into X and Y. But here's what happens. You have three similar triangles from drawing that altitude. So first, you have the smallest triangle with this angle right here at B. And that is this triangle right here. So here we have X, A, and H as its sides. It's triangle CHB. And from that, we know it's similar to these other ones because let's take the second one for example. We know that this is an altitude, so that has to be a right angle here. And we know that this angle down here is, let's put 3 here, is its own thing. But if these two angles add up to 90, and these two angles are supposed to add up to 90, then we have that this angle is congruent to this one. And the same goes for this one. If these two add up to 90 because of 90, this, and that, which have to add up to 180, and these two add up to 90, then we know that that is like that. So that's why from here you have angle, angle, angle. And that shows these two similarities. And then we have the entire triangle itself, which is right here. And it's basically for the same reason. You have this 2 angle at B, and then this 3 at A. So by angle, 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 it's similar to the other two as well. Now we move on to our next topic, which is the angle bisector theorem. And basically, an angle bisector is a line that cuts an angle in half. And there's a special thing in a triangle when it comes to the angle bisector theorem. And that is that an angle bisector divides opposite sides into two segments whose lengths are in the same ratio of the sides adjacent to them. Now that might be a bit confusing, so I have a picture and a little formula. So we have triangle ABC, and in that we have angle bisector AD, which bisects angle BAC into BAD and DAC. And from this, we get that AB divided by AC, so AB divided by AC is equal to BD over CD, or BD over CD. So this over this is equal to this over this. Or in other terms, AB over BD is equal to AC over CD. An easy way you can remember this is that think of this as being cut into two triangles. Outside and the one that's cut. And it doesn't matter which one's on top, as long as you have the same ones on top. So outside AD over the one that's cut, BD, or outside AC over the one that's cut, CD. Another way you can do this is start from your top point that has the angle bisector, and you have your two lines connecting from it. Take those two lines and do AB over AC, and then you do the corresponding one, so BD over CD. Now we move on to the last part of two-dimensional anything we have today, I think, which is Heron's formula. And basically, Heron's formula is a formula that you can use to find the area of a triangle. Let's say the triangle is too weird to figure out the base and the height. You use Heron's formula. So what it says is that area is equal to the square root of S times S minus A, which is side 1, S minus B, side 2, and times S minus C, which is side 3. And all of this gives you the area. So to show you how this works, let's do an example. Also, S is the perimeter divided by 2, or A plus B plus C over 2. So to show you how this works, let's do an example. We have a common right triangle, which is a 3, 4, 5. We already know that the area is 6 units squared because 3 and 4 are the bases. 3 times 4 is 12, divided by 2 is 6. But let's try it with Heron's formula. If we use Heron's formula, we figure out that S is 6 because it's 12 divided by 2, which is 6. And then we plug it in. So we have 6 times 3, 6 minus 3, times 2, which is 6 minus 4, times 1, which is 6 minus 1, 6 minus 5. So all of this gives you the square root of 36, which is also 6 units squared. And they're the same, so this shows that it works. Now we move on to the final part, which is 3D geometry. And in that, we have a few vocab terms. First off, polyhedrons. Polyhedrons are geometric shapes made up of polygon faces which meet at straight line edges that come together at vertices. So faces are basically the flat surface of a polyhedron. Edges are where they meet, or that is, faces are 2D, edges are 1D because they're line, and vertices have no dimension because they're the points that the edges meet up. And then we have platonic solids, which are regular polyhedrons with congruent polygon faces, meaning it's like the 3D version of a regular polygon. And we only have 5 platonic solids: a tetrahedron, which have 4 equilateral triangles, a cube, which has 6 squares, an octahedron, which has 8 equilateral triangles. You can remember that by octa. A dodecahedron, which has 12 hexagons, so dodeca means 12, deca means 10, and then isocahedron, which means 20 equilateral triangles. So now let's move on to more 3D geometry. So there is a written rule for all polyhedrons that the number of faces plus vertices is equal to the number of edges plus 2. To show you that, I have a nice table here showing our 5 platonic solids and showing you that it works. So a tetrahedron has 4 faces and 4 vertices. 4 plus 4 is 8. It has 6 edges. 6 plus 2 is 8. They're equal. I'm just going to show you this for this one, and then I'm just going to go through the rest. So a cube has 6 faces, 8 vertices, and 12 edges. And you can remember the 6 faces because it's a common die. And then we have an octahedron, which has 8 faces, 6 vertices, 12 edges. And then the dodecahedron, 12 faces, 20 vertices, 30 edges. And then isocahedron, which has 20 faces, 12 vertices, and 30 edges. You can remember these two because they're basically switched. For the faces and vertices, you have 12, 20, 20, 12. And the number of edges are the same. The same thing goes for the cube and octahedron. There's 6, 8, 8, 6, same of edges. Now let's move on to types of polyhedrons. We start off with a prism. A prism is a polyhedron with 2 congruent bases connected by parallelograms. For example, we have a rectangular prism, which are the bases in this case are rectangles. Now we have a cube, and which is this right here. A triangular prism, which are 2 triangles connected by 3 parallelograms. And then we have this hexagonal prism. I tried drawing that, I failed, but the bases are 2 hexagons connected by the sides, which are parallelograms. So in this, the volume is equal to BH, and where B is the area of one base, and height is this line here. So that's how you figure that out. While surface area is equal to the perimeter of the base times the height plus the area of the 2 bases. Then we move on to a cylinder, which looks like this. It's basically a prism with a circular base, meaning it's not connected by parallelograms. It's connected by like a covering. If you think of a paper roll, when you unravel one layer of a paper roll, it's a rectangle. So that's how it's connected. And its volume is pi r squared h. Pi r squared comes from this base, and height comes from those unit circles, and that's the height, like the number of those unit circles in that. And then the surface area is 2 times the base plus 2 pi r squared h. It's 2 pi r squared h because the circumference of this is 2 pi r, and you want to multiply by h. And now for our last polyhedrons. We start off with the pyramid, which is which has a polygon face, while all the other faces are triangles that meet at a common point. I tried to draw, these are two triangular pyramids, and this is a square pyramid. You might remember pyramids as from like the pyramids of Giza. That's a good example of pyramids. And basically, in a pyramid, the volume is 1/3 base times height, where base is the area of base and the surface area is the sum of the area of all the faces. Then we move to the cone, which is basically a pyramid with a circular base. And that's how it looks. You can think of a waffle cone. Waffles are good. And its volume is 1/3 pi r squared h. Its surface area is pi r squared for the base plus pi r s. S is the slant height here. It's not from the point to the center. It's from the point that they connect at to any point on the circle, which is slant height. And then we have the spheres, which is the collection of all the points equidistant from the center. So that sounds a lot like a circle, but a circle is only two-dimensional. But a sphere goes in all three directions. So that's why it looks like this. It's like a ball, or the sun, or any star. So its volume is 4/3 pi r cubed, and its surface area is 4 pi r squared. Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end.